Quantum computing sounds like something out of science fiction, but it's real, and it's already starting to reshape the future of technology. Confused by all the talk about qubits, superposition, and spooky science? In this video, we're breaking down what quantum computing actually is, in simple, clear terms, and why it matters more than you might think. Before we get started, don't forget to like, subscribe, and hit the notification bell for more easy tech explainers. Let's unravel the quantum mystery, starting now. What makes quantum computers different from regular computers? Your laptop processes information using bits, tiny switches that are either on or off, representing 1 or 0. Every calculation, every video you watch, every message you send gets broken down into millions of these simple on-off decisions. It's like having an army of workers who can only answer yes or no questions, but they work together incredibly fast to solve complex problems. Quantum computers throw this rulebook out the window. Instead of bits, they use quantum bits or qubits. Here's where it gets mind-bending. A qubit can be 1, 0, or both at the same time. This seems impossible because it violates everything we know about the physical world. But at the quantum level, particles behave in ways that defy common sense. Think of it like a coin spinning in the air. While it's spinning, it's neither heads nor tails. It's both possibilities existing simultaneously. Only when it lands does it become definitively one or the other. Qubits work similarly, existing in multiple states until they're measured. The quantum advantage: superposition and entanglement. The real magic happens through two quantum phenomena: superposition and entanglement. Superposition is what allows qubits to be in multiple states simultaneously. While your computer's 8 bits can represent one number from 0 to 255 at a time, 8 qubits can represent all 256 possibilities at once. This exponential scaling is staggering. Just 300 qubits could represent more states than there are atoms in the universe. This means quantum computers can explore millions of solution paths simultaneously, rather than checking each one individually like traditional computers. Entanglement is even stranger. When qubits become entangled, measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance, but it's real and measurable. Entangled qubits share information in ways that allow quantum computers to perform certain calculations exponentially faster than any classical computer ever could. How quantum computers actually work. Building a quantum computer is like constructing the most delicate machine imaginable. Qubits are incredibly fragile. They lose their quantum properties when disturbed by heat, vibration, or electromagnetic fields. Most quantum computers operate at temperatures colder than outer space, near absolute zero. The quantum computer doesn't run programs like your laptop. Instead, quantum algorithms manipulate qubits through carefully choreographed sequences of quantum gates. These gates rotate qubits through different quantum states, creating interference patterns that amplify correct answers and cancel out wrong ones. When the calculation finishes, the qubits collapse from their quantum superposition into classical bits that we can read. It's like conducting an orchestra of quantum particles, where the final measurement reveals whether the symphony produced the right answer. Real-world applications that will change everything. Quantum computing isn't just faster computing. It's fundamentally different computing that excels at specific types of problems. Drug discovery represents one of the most promising applications. Molecules are quantum mechanical systems, so quantum computers can naturally simulate how different compounds will interact with our bodies. This could accelerate the development of new medicines from decades to years. Cryptography faces both opportunity and crisis. Most internet security relies on the difficulty of factoring large numbers, something that would take classical computers millions of years. Quantum computers using Shor's algorithm could break this encryption in hours, potentially compromising everything from banking to national security. However, quantum cryptography also promises unbreakable security through quantum key distribution. Artificial intelligence and machine learning could be revolutionized. Many AI problems involve searching through vast solution spaces, exactly what quantum computers excel at. Quantum machine learning algorithms could identify patterns in data that classical computers would never find, leading to breakthroughs in everything from climate modeling to financial prediction. Current limitations and challenges. Despite the excitement, quantum computers face significant hurdles. Quantum decoherence means qubits lose their quantum properties within microseconds, limiting how long calculations can run. Current quantum computers make errors frequently, requiring complex error correction that needs hundreds of physical qubits to create one reliable logical qubit. Most quantum computers today are proof-of-concept machines that can only solve specially designed problems. They're not general-purpose computers and won't replace your laptop. Instead, they'll work alongside classical computers, handling specific quantum-friendly tasks while traditional computers manage everything else. The technology is also incredibly expensive and complex. Quantum computers require teams of PhD physicists to operate and maintain. However, cloud-based quantum computing services are making the technology accessible to researchers and developers worldwide without requiring them to build their own quantum labs. The timeline. When will quantum computing matter? Quantum computing is currently at a critical turning point in its development. Leading companies like IBM, Google, and others have demonstrated quantum advantage for certain specialized problems, showing that quantum processors can outperform classical computers in specific tasks. For instance, Google's Sycamore processor famously achieved quantum supremacy by completing a calculation in just 200 seconds that would take the most powerful classical supercomputers thousands of years to solve. However, some experts debate the practical relevance of this milestone, noting that it involved a highly specialized problem with limited real-world applications. Looking ahead to the next decade, quantum computers are expected to begin addressing more practical and complex challenges, particularly in fields such as logistics optimization, financial modeling, and advanced manufacturing. Beyond computation, emerging quantum sensors promise to revolutionize areas like medical imaging and precision navigation by leveraging quantum phenomena for unprecedented sensitivity and accuracy. Still, the full transformative impact of quantum computing, such as breaking current encryption methods, accelerating drug discovery, and dramatically enhancing artificial intelligence, is likely still 10 to 20 years away. The global race to develop quantum technology is intensifying as governments around the world pour billions of dollars into research and development. Nations including China, the United States, and the European Union recognize quantum computing as a strategic priority, understanding that achieving quantum advantage could redefine global technological leadership and economic power in the decades to come. Quantum computing may be complex, but the idea is simple. It has the power to solve problems too big for today's computers. The future is weird, and it's arriving faster than we think. If this made quantum computing feel a little less confusing, drop a comment and let us know. And for more Tech Made Simple, don't forget to subscribe and hit that bell. Until next time, stay curious.